So hello everyone. This is our group project for the SC401 Elements of Cryptography course. We have done our project on zero knowledge smart card identification, and our project is mainly aimed at theoretical physics. So this is our team. The team consists of me, Nisarg Suthar, Manjal Shah, Pathik Patel, Harshit Vadodia, and Isha Popat. And these are our contributions. So what we are going to cover. So first of all, we will state our objectives. Then what is identification? What are zero knowledge protocols? The Fiat Shamir protocols and its subtopics, the smart cards, the extensions and future scopes of our project, and finally conclusions. Okay. So what are our objectives? So we need to understand why we need identification schemes first of all. Then we will understand the drawbacks. Then we'll go on to understanding the zero knowledge proofs. Then we will come to the main part of our project, that is the Fiat Summary protocol. Then we will be analyzing the protocol, and then finally we will be showing you the implementation that we have done in Python. Now, identification. Who are you? So, okay. So when you are logging into a PC, paying at a mall via credit card, or drawing cash at withdraw at ATMs, or every time you need to prove your identity, you need to tell the system who you are. So the objective of identification scheme is to enable someone to confirm their identity. So what are the common identification schemes? The common identification schemes are based on what you are, so the attributes and behavior of yours, or either what you have, some documents or credentials, or what you know. So something private knowledge that you possess, like PIN or password. So all these identification schemes have certain vulnerabilities and are susceptible to brute force attacks, in which they try to just guess your password. Then there are dictionary attacks where hackers have a large dictionary of commonly used passwords. And then there are phishing attacks where the hacker tries to impersonate someone else and take your password. So all these schemes are vulnerable because you need to give your password at some point of time. Hence, we need a protocol in which you don't require to give your password at all. So there comes the need of zero knowledge protocols. So now the zero knowledge proofs, a proof without one. All right. So this is the overview of the zero knowledge proofs. So what are zero knowledge proofs? They are an encryption scheme which were proposed in the 1980s, and it involves proving a system without actually revealing any information. So why we need zero knowledge proofs? Because they are used in authentication, data privacy, transaction verification, and decentralized system. So how these zero knowledge proofs work? If the prover wants to try something to a verifier, the verifier then throws a challenge to the prover, and the prover has to respond something to the verifier, and then the verifier decides whether the response was actually coming from a prover who claims to know the knowledge. Okay. So this way, the prover verifies the hidden information that he has without actually revealing the information. So life is all about soundness, completeness, and zero knowledge. Okay. So soundness, completeness, and zero knowledge are the properties of a zero knowledge proof. So what soundness does is it ensures the security and reliability. So for a false statement, if the prover is trying to prove a false statement, then the protocol should state that it is a false statement. Now we come to completeness. What completeness ensures is that a true statement should always be given as a true statement. Without completeness, a proof system is completely useless. Like if even if that statement is true, if the system gives false, then what the use of this protocol is? And the main part, the zero knowledge. The proof should not be revealing anything other than the thing we are trying to prove. We are trying to prove that we possess the knowledge of something. So that does not mean we have to share what we know. We only have to prove that we know something. All right. So the verifier should be convinced of the truth of the statement without actually learning anything new about the statement. So a simple toy example to let this concept sink in is the example of where is Waldo. So suppose, as you can see on the slide, here is Waldo on the left, and there is a picture of a Mela where you have to find Waldo, where Waldo is. Now, if somebody is knowing the position of Waldo, what he can do, that he can show that he knows the position of Waldo, but uh, does but without revealing where actually the position of Waldo is to the other people. So what he can do is he can put a cardboard piece, a large cardboard piece over this picture of the Mela, and just put a pinhole in the cardboard and ask the other users to see through the pinhole. And from the pinhole, they can view the picture of Waldo. But since because of the cardboard, you don't know whether Waldo is on the left or right, top, bottom, middle. You don't know behind the cardboard. The only thing behind the cardboard you can see is Waldo. So this is how you can prove that you know the position of Waldo without actually revealing the position of Waldo in the picture. So now let's come to the Fiat Shamir protocol. It is also known as the fish protocol because of P from Fiat and SH from Shamir. Okay, so what is the fish protocol? The fish protocol allows the user to convince a verifier that they possess the knowledge of a secret value without actually revealing those secret values. So it is based on the knowledge of a one-way function, which is easy to compute in one direction but hard to invert in the reverse direction. So here we have a prover, which is known as A, and then we have a verifier B. The verifier B sends a challenge to A, to which the prover A responds. So here we come to the protocol. Suppose f is a function for some small values of j. Like here, I is the information that the prover A possesses, and j are some index values. So now we have to pick k index values for which vj, which is also some value, which possesses the property that it is a quadratic residue mod n. N is a large string of product of primes. So at the minimum length of n should be 512 bits. Now we go on to computing the smallest square roots as sj's of the vj inverses. Then after doing this initial work, we go on to the exchange between A and B. Now what A does is A sends I to B, I to the actual authority, and then B generates the values Bj for the J's. Now another steps are computed iteratively computed t number of times. So what happens over in this iteration is A generates some random value Ri and sends Xi equal to R square to B. After receiving the R square, B generates a random vector Ej, which is very important. And B sends this to A. Now A computes Yi's, which is given on the slide, and then sends this Yi to B. Now B verifies whether the Xi that was sent by A actually matches the computation Yi square product of Vj mod n. If it matches, then B responds with a truth. Yeah, it is verified. And if it does not match, B responds with that the claim was not verified. So usually the value of k is between 1 and 80 and should be, as I said, at least 512 bits long. And B accepts the claim only if and only if all the T checks pass. Now, why this protocol works? Like, so from the definition, you can see that yi square product where ej equals I, bj is equal to r square times the product of where eij is 1, sj square vj is equal to ri square. Why this happens? Because sj square is actually the smallest square root of the vj's, inverses of vj's. So this product comes out to be 1. And r square is the thing that a signed to be in the first place. So this left hand side is equal to the xi mod n. Hence, B satisfy the criterion and B responds with the truth. True that the claim was verified. Now, if we think that suppose A wanted to cheat, then A would cheat by guessing the vector Eij that B sent to it. Now, in guessing this vector, what happens is it is a vector of k length. So there are 2 raised to k possibilities of the vector. So the probability that the guessed vector is the actual vector is given by 1 upon 2k. And for if we repeat this for t iterations, then the probability goes down as 2 raised to minus k. So to put this into perspective, if an adversary uh, tries to actually guess it, then he won't be able to, because even for small values of a and t like 5 and 5, the probability goes down as 1 upon 2 raised to 25, which would be a very, very, very large. Now, if we suppose that suppose an adversary is there which has like gained the responses from A. This is a totally different scenario where an adversary has tried to gain all the responses from A after running the protocols for a polynomial number of times. And now what the adversary does is he tries to replay or misrepresent himself as A by giving those pre-recorded values again to the verifier. But here also there will be a problem because every time B sends EIJ, it generates the EIJ vector fresh. So again, the possibility that the answer from the replay of A matches the answer that a verified user would give will again be 1 upon 2 raised to minus kt. So again here the probability is very less that a false verifier would come out with a true verification. So suppose now to give an example, if a fiend, like not a friend, fiend, is trying to misrepresent himself even 10,000 times a day, he will still require 3,000 years to succeed even once, and by which his 300 generation might have died. So it is quite impossible to uh, prove a false claim over here. Now let us adapt this protocol to smart cards. So what are smart cards? They are cards like your credit cards, your ID cards, your debit cards, or any other ID cards that you might have. So, what the smart cards would contain over here? The information string and the SJs, which were pre-computed and are stored in the smart card. Now, what the verification devices would look like? The verification devices, as you might have used the credit card swipes at malls, they are standalone. Here they store just the modular set and the function app. They have a microprocessor, so they can do small computations. They have a limited memory and then IO interface. Now, what we have to do? We have to prove the knowledge of SJ without giving away any information about its values. So now let us get into the implementation that we have done in Python language, and we have used OOPS for doing it. I am damn sure that no one has implemented this protocol using OOPS ever before. So now we will go to the code and demo. So um, here we have used Colab to implement our code. Okay. So here are the library imports. Then here we have just implemented the protocol. So this is the prover class, this is the verifier class, this is the identify wrapper class, which actually has the verify function. Then we have a test run of the code. So here is the completeness and the soundness check. Completeness, as I explained, a true statement should be given as true, and soundness check is how many false statements were classified as true. So a 0.92 values of soundness check means 0.08 proportion of times a false claim was regarded as true. So that is very small because that is very small compared to the number of times a true value is given as true. Now we come to the smart card implementation. Here I have created a class authority, which has a user class as the subclass. So only a authority object can create a user class. And again, here are the usual functions like verify, calculating the function f, assigning, initializing with the sj values and all. And here is the test run of the code. And here, since I have kept the values of k and t very small, like uh, 3 and 1, so the soundness check would give probability of 1 minus 1 upon 2 raised to 3, which is very close to 0.7. Now to here I have just generated the theoretical results like the soundness, which should be around 1 minus 1 upon 2 raised to minus kt. Okay. So this was the implementation of the code, and we have also created a user-friendly uh, UI to actually run our code. So here I am creating a authority. So we will keep the bit length as 8 just to uh, give a toy demo. K to be 2 and length to be 2. I create the authority. Now let's see the authorities. Here is the first authority. I'm creating a user, and I say the user is a cheater. Now I create another user, and this is the actual user. So if I test whether this user is a cheat or not, yes, it's a cheater. And if I test this, yes, it again was a cheater. All right. Okay, so now let's go back to our presentation. Okay, so these are the results that we obtained. So the protocol soundness, as I said, is expected to increase exponentially as the product KT increases. This is because, as we have seen, probability of a cheetah succeeding goes down as 2 raised to minus KT. And these are the results. So you can see if K and T are 1, 1. So the probability would be 1 upon 2, which is around zero point 0.5. So that's why you are getting close to zero point 0.5, which is 0.49 as the soundness value. And same way you can verify the other values as well. So now we come to the extensions and future works that we could do. So actually we can have different levels of security which can be determined by K and T. So for example, suppose if you want to identify someone for the gate pass, so you can keep small values of K and T. Just so that the identification identification process becomes very fast. Because on gates you don't need that much uh, uh, confidence that a person has actually verified his identity or not. But while there might be some sensitive areas like meeting rooms and all, where you really need to be sure that the person entering is actually the person that is identified, there you can keep high values of KNT so that the confidence of proving the identity of the uh, authenticator is very high. Okay. Then another thing that we can tweak is we can, instead of quadratic residues, use cubic residues. And then we can also make the EIJ vector as non-binary. Okay, so that were some of the tweaks that we could do. So here are some concluding remarks. The Fiat Shamir protocol is so powerful tool for proving the knowledge of a secret value without revealing it. Then we can also use, like, we can adapt this protocol for signing digital signatures and for authentication. Now, uh, if factoring is difficult, one can actually prove that this type of scheme is probably secure. And also due to the simplicity and security and the speed that this protocol provides, this type of protocols are very aptly suitable for microprocessor based devices. Like you have your smart cards, obviously, some PCs, and also some remote control systems. So here are our references. And yeah, that's all from our side. I hope you like our project. We actually enjoyed doing this project.